Today, we're very honored to have our IAS distinguished speaker, Professor CK Law from Princeton University and Tsinghua University with us here today to talk about some recent advances in fundamental and transdisciplinary combustion. Professor CK Law got his PhD in engineering physics from the University of California at San Diego in 1973. He then joined GM Research Laboratories as a research engineer and furthered his career in Northwestern University as an associate professor and at the University of California at Davis as a professor. He then moved on to Princeton University, where he is currently the Robert Goddard professor. Professor Law's research focuses on combustion with applications in propulsion, energy, and environmental studies. He will talk to us today about a range of different issues relating to fundamental and transdisciplinary combustion topics. So
I see that Professor Lee is introducing our speaker with his backpack. So, very dutiful. But colleagues and some of our students, I'd like to take this opportunity to say a few words. Introduce Ed, Professor Law. Ed and I, we are friends for a long time. A very special friend. That's why I would like to say a few words so you can get a little bit more sense in terms of not just what kind of research he does, but how he does research. As Professor Lee mentioned earlier, Ed's first job was with GM Research Lab. Okay, and I read some of his papers when he was a GM, and I was a student. Okay, and at that time, Ed and his collaborators did some very fundamental research, droplet and laminar flamelet, and so on and so forth. So some of this work have become defining knowledge in the field. And if you look at Professor Law's entire research spectrum over the last 4+ decades, combustion certainly is a defining theme, but it's much more than combustion per se. And more importantly, I would say Professor Law's work is always at the very forefront of combustion science. Combustion is a very large field. Okay, if you look at the combustion symposium, the proceedings, so many papers, and more than half the papers were rejected anyway. Okay, so it is very, very competitive, highly diverse subject area with long-standing, dating back to some of the earlier books was more than a century old. Okay, but in that context, if you have not read it, I highly recommend you to get a copy of the book he authored, published by Cambridge University Press. This is a big book, size as well as in scope. Okay, it has all the rigor and all the analytical skill and the physical interpretation of combustion science. The other thing that Professor Law did is related to space. And microgravity is one of the defining physical mechanism which makes it different from Earth-bound environment, and hence some of the very distinct combustion phenomena when you observe up there can be quite different from what we see down here. And Professor Law for many years was leading many researchers funded by NASA at the time to address this very important topic of combustion under a microgravity environment. So the list goes on and on, but today we are in for a treat to see some of the most recent work Professor Law has done. And after this, maybe we'll have a drink to talk more, okay? Thank you.
It's really a pleasure and honor to be here, to share my thoughts with you guys. And again, thank you, Professor Lee and Professor Wei Shi. And Professor Wei Shi and with me, we go back a long time. And it was just so, I just so feel excited and so impressed as I walk around the campus and see that a lot of activities and creations, thanks to Professor Wei Shi. I think the university is fortunate to have recruited Wei Shi here. It's just marvelous. That's all I can say. So anyway, what what I wanted to talk about when I was asked to give a seminar. I think maybe I'll give some sort of general view of combustion. So to just give the student a rough idea of what intrigues me and what maybe the future of quote-unquote combustion was like, okay? So I have this topic, fundamental and also transdisciplinary, that seems to cover everything. You have to do that for me too. So, okay, let me go. Okay, so I could not resist because this is the poster designed by you guys, okay? And it was so impressive, so I have to put it here. The earth on fire and all that. I think I'll use it in my other talks later. I have to wipe out some of the things, but I'll do it. Yeah, I have to. That's probably copyright. I don't know. I'll see it. So, all right. Let me go. So what's the content of my lecture? Let me go a little bit further. I don't want to block your view. So, sort of talking sort of in general sense. So maybe we'll talk what is combustion, right? And I talk about core discipline and then expand the view. Then I go so selected topics of core combustion, what it is, but examples of transdisciplinary combustion as related to topics of core. How I structure my talk. All right, so what is combustion, right? So let's just see. So combustion, I say it's a major scientific discipline, all right? So first of all, combustion is study of chemically reacting flows. It's a sort of simple 3 letters, but it really indicates the complexity of combustion because it includes chemistry, includes flows, all right? And so those are the 2 really very challenging aspects. Now, if you think of flows, one example you can see that Professor Weishi just talked about microgravity combustion. If you look at candle flame, here's a typical candle flame on Earth with natural convection, right? The flame gets elongated. But then when you go to microgravity, no gravity, there's no natural convection, the candle flame is like this, all right? So there's nothing here. And so, and then what you see is also the change in color. This is all yellowish, this gets blue. All right? So this yellow, anyone who works in combustion know that when you see yellow, it's soot, okay? Things like that. But when you see it, you have no soot. All right? So again, your residence time, your comparison of flow time and chemical time and all this, they all come into issues. And then there's another one, of course, right? It's oil or the flare in an oil field, and then they go out. You can see that there's natural convection, maybe there's wind blowing and all that. It's highly turbulent. And then again, the soot is formed here. Right? So that's what it is. So combustion is multi-physical sciences. And then, again, as I said, it's embodying 2 major branches of nonlinear science. I emphasize the word nonlinear, right? Chemical kinetics and fluid mechanics. When things are nonlinear, that's interesting. When things which is linear is not too interesting. Linear, you give one, they give you. Non-linear, you get things turn around and all that. Right? That's what the thing is. So combustion is also a multi-scale science. Right? You can, if you look at different time scale, length scales, and time scales, you can go to very fundamental level, the quantum mechanics, all right, in calculating the molecular structures, the detailed structure, the electronic and intramolecular interactions, and then molecular rearrangement, going to, for example, formation of nanoparticles, soot and PM2.5. Eventually, you're going to turbulent fuel mixings. Your scale can really go very, very large. So from that point of view, this, it's a very rich area, and it's also a major technology drivers, right? If you think of it, it's pollution and climate, obviously, right? There's energy, the beautiful, I think, Hong Kong harbor, right? I'll pick that for you guys. But all this, it all comes from mostly from combustion, okay? Because the electricity, where you get the electricity, you have to burn things. Mm-hmm. So the fuels, okay, right? I mean, it's a major area that a lot of combustion people end up work for oil companies. How to do that? And the defense, no doubt, by the thing. And space, the rockets. I don't know how you guys feel. Every time I see, right now there's not too much launch now, but every time I see a launch of this Apollo 5 and this rockets, you feel the power of the science lifted up so much. It's incredible. I just get thrilled every time. Combustion, of course, is some cause of trouble. Smoking, all right? This guy might feel very happy, right? But actually, he's causing trouble, right? It's a slow combustion, smoldering, okay? You still got chemical reaction and flows. And if you think, if you can, people always, if you can design some smoking, the products are actually be good for your health, wouldn't it be wonderful, right? Rather than hurting you. So, and then, of course, safety. Safety, you got this industrial explosions. Something explodes, couple of seconds, yeah, everything goes. Right? So all these are really, truly relevant to our daily lives. So those are what it is. And then for some time that myself and some of my friends, we've been sort of advocating, we want to expand the frontier of combustion. When you do research, it's one thing you do, but although at the same time you say, how I can do more. That's what makes life interesting, right? Okay? So how to expand the frontiers? Well, there are two groups of sort of expansion I can think of, okay? One is looking to extreme combustion, right? Your expansion of the scales, right? For example, what I said, microgravity combustion and the space combustion, right? You go to microgravity combustion is what I said without buoyancy or something. And in space combustion, I might say something later, for example, in a supernova, right? Explosion of stars. You go to the S, and actually later I say that. And micro engines, right? You have some very tiny really engines, right? People are thinking of building small thrusters for the satellites so you can position them, very fine positioning thrusters. Let's think of something, small engines put in your body and they go inside and clean up your body, okay? Things like that. And micro engines are burners. Then, of course, there's supercritical combustion, thermodynamically. There's always one problem in combustion. People always talk about it, never really critically study it, is high-pressure combustion. Internal combustion engines, the pressure is very high, all right? So the thermodynamic state can go to supercritical. You don't have ideal gas laws and all this, everything breaks loose. And how to do it properly, right? Under high pressure. And high pressure combustion is important because it's make the combustion more efficient. Right? It's supercritical. And of course, supersonic combustions. All right? So you get micro, it sounds good, right? Super. Now, so that's one part. Actually, this part I may not talk much. Now, the transdisciplinary combustion. Your expansion of the reactive and flow system. What I was saying is that combustion, just then I say it's chemically reacting flows. Chemically reacting flows. I take the chemistry away. Reacting flows. Okay? So I claim that also combustion. Just reacting flows. What kind of reaction? I mean, you can go to all different kinds of things. You go to astrophysical systems, all right? Then what's the reaction? Nuclear reactions. All right? Things happen in supernova. Right? Those are nuclear reactions. Right? You can look into that. Why not? Of course, biological systems. Right? That's a biological reaction. Of course, again, chemical system. It's kind of nice ABC here, but I cannot find D. But anyway, so there's nuclear system and the societal system, society. So I'll cover some of it, okay? So, and more. All right. So what I want to, now we come to the topic of presented. So basically core combustion, all right? I just want to, basically the kind of phenomena I'm talking about, mainly combustion phenomena. So it's typical problem. If you think of, this is sort of really cartoon. If you have a spray of a fuel coming into here and they mix with air and then they burn. Then you get liquids, they break up into droplets, okay, here, and then they vaporize But then the droplets might get close enough, they can interact with each other, collision, and then they mix with each other, and then you have some flames, and the propagation, and then I'll talk about the propagation morphology of expanding flames, all right? How the flame surface behaves. It's rather interesting. And then, so there's complex chemistry. The chemistry goes crazy, right? So how do you reduce the complexity of chemistry, reduce order chemistry, right? And then for CFD, to do computational fluid dynamics. All right? If you don't do this kind of reduction, there's no hope you can describe chemistry in combustion flows. And then we go into the detonations, dynamics of detonations. All right? So some of this, they are subsonic flow, the supersonic flows. All right? So we cover the area of fluid mechanics very extensively. So then the examples, this is the core combustion, and then each one of them are taken to some kind of example of transdisciplinary combustion. Talk about inkjet printing, okay? Talk about medical injection. Talk about material synthesis, inertia confinement fusion, societal networking, supernova. Isn't it fun? Look at all this. I'm not explaining any of them, okay? But I just want to tell you this is fun. Right? And then if you have time, so go into it, maybe you can get some new insights into the problem. All right. Okay, so let's go one by one. Dynamics of droplet collision. So what you have the core interest here. Now, again, in sprays, in diesel engines and all this, you inject your liquid fuel as a spray of droplets. All right? The droplet dynamics, when you inject them here, they are there. But in the dense spray region, the dynamic side, they basically control the combustion response of liquid fuel combustion. Right? But then, after you generate the droplets, they actually could collide with each other. They are dense, they're very close, and the flow here could kick them around. They'll collide. And then after they collide, what happens? Right? If they collide and coalesce, then you change your spray statistics. So then they can significantly modify the spray characteristic. Right? So, and this is not just in combustion, in other systems, in your sprinkler systems, your insecticide spraying, and all this. So what I want to discuss with you, say first of collision between identical droplets. Okay, reference scenario and controlling mechanisms. Okay, let's look at this. So here it's a busy figure, and I just want to show you some global response. Okay, under just atmospheric pressure. There's some results on water. There's results hydrocarbon. Let's look into hydrocarbon burning. Just head-on collision. Right? Let me just show what happens. So if you have two droplets hitting each other this way, tiny droplets. At 100 micron, for example. So they come here and they get close to each other. You see the deformation here, and then eventually they merge, okay? They merge. And then when they merge, they don't just right away become spherical. When they merge, they will oscillate a little bit. This way, that way. Why do they oscillate a little bit? Well, they have to oscillate a little bit because from energy conservation. Because beforehand, you have two droplets with surface tension. Each one has surface tension. When they become one, you also have surface tension. And that surface tension is much less than the two individual ones. So you have to dissipate away some energy. And then you dissipate away, so it oscillates. So there's internal motion inside the droplet, which would dissipate. So the collision and merging phenomena is inherently inelastic. You cannot treat it as elastic. Okay, so those are things. So that's one observation. And then of course, if you increase the impact inertia a little bit more, then they won't merge. Okay, they won't merge. Then they bounce. Now, if you increase it some more, okay, they will bounce. But you increase some more, then they merge again. Okay, so merge, bounce, and merge again. All right? So it's a non-monotonic behavior. So what you see here is that if you just look at this one, sort of the Weber number is the indicator of impact inertia relative to the surface tension. And then you see this merge, bounce, merge. Eventually, it'll break up into some more droplets. But anyway, you got this non-monotonic behavior. Now, what is interesting with this hydrocarbon droplet? What is interesting with water is that there's no this region, okay? There's no this bouncing region. It's just always merge. What happened when we initially studied this is that people have been studying droplet collision, but it's all based on water because of meteorological interests. People are interested in the raindrop formation. Raindrop formation is you form the droplets up there, they come down, they hit each other. That's how they grow. So they all use water. But then we are interested in engines, so it's in fuels, right? So, okay, we just want to repeat some experiments, but then we suddenly saw that there's bouncing here. So it's qualitatively totally different, all right? So what's the reason? So there are several issues here. So what is happening is that is this bulk droplet dynamics, they affect the bouncing and merging. You see, when you have two droplets here, they hit each other. When they hit each other, there's an air gap between them. This air gap, you have to push out the air. And it's not easy to push out the air, all right? So there's this finite drainage rate of this one upon approach. Okay? So when you want to push it out, there's a pressure buildup. A pressure buildup, then they'll cause droplet deformation. All right? So this droplet will deform, they will absorb this impact inertia to prevent it from merging. All right? So there's more surface tension. So this, and then through that, then of course there will be extensive internal motion because of this deformation and this. So, so then the obviously is whether you can push out this layer. Okay, if you can push out this layer, then they will merge. If you cannot, then they will bounce. All right? So that's the challenge. And the problem here also is that for the two interface to merge, they have to get close to the molecular distance range so that the molecules can start attracting. A van der Waals force. All right? So the flow here, Professor Wei Xu would appreciate this kind of problems because you're talking about rarefied flows, okay, in here. So you have continuous flow here, but then in the end you have to trace through all the ranges from continuing to rarefied flow to even molecular range. And to do that, okay? So that's basically the challenge, even in fundamentally trying to solve this kind of problems. And this is actually the problem that people are still trying to do it. It's, we have Professor Losi from Trento, who was just visiting Tsinghua. By the way, he's the second Bachelor Prize winner from the Netherlands. He's very much interested in this kind of problems. So the relevant physics is that, I talk one, two, three. If you want to describe them properly, you have to go with continuum flow, rarefied flow, free molecular flow, going to van der Waals force. Okay? So many decades of lengths. So your droplet size can go to 10 to the 10 to 3 micron. Mean free path is 10 to the minus 1 micron. Molecular force distance. So here's those are the challenges. So we have done formally some theory, not really totally complete, but then the whole theory is you need to have Newton's law of motion for the mass transfer, right? You need to have mass conservation and energy conservation. You need to allow for surface energy, viscous laws, and then you need to allow for internal motion, and then you need to have rarefied gas flow, and you need to have surface molecular. Right? So the problem superficially looks kind of simple, but actually it's a whole slew of physical phenomena. Yeah. So we did we basically did the analysis at a very small scale, and then basically end up with some ODEs, then you can solve it rather nicely. So what's happening is that, for example, water, if you plot the interfacial gas width as was a function of time, when you impact them, eventually they will merge because the interfacial distance will go to 0, they'll merge. But then, so that's for water. Remember I told you water, they will always merge, okay? But that's at one atmosphere. If you increase the pressure, right? So we thought that, well, what's the difference between water and hydrocarbon? They're all liquids, right? It has to be similar, right? So, okay, so let me make water to also bounce and make hydrocarbon droplet to also merge. See that? Okay? So that's how you do the flip-flop experiments. So then we do the water droplet if I increase the pressure, okay, for water droplet. Before they always merge. Now, if I increase the system pressure to 2.7 atmosphere, for example, then they bounce. Right? Because there's more pressure, so it's just harder to squeeze them out. And similarly for the hydrocarbon, as I said, in one atmosphere, they will merge. But if I reduce the pressure, they will bounce, okay? They'll bounce and merge. If I decrease the pressure, then they'll. Right? So again, we resolve the dilemma. Right? So, you know, it's not a big deal. You just change the atmosphere. So the calculation, but also experiment, we've seen this. So, you know, that's something fun with doing research sometimes when you try to resolve things. A lot of times, just you flip the thing, flip-flop, and a lot of times it's very simple, really. Once you see the physics, just do it, and it shows. Right? But, it can be explained just by a few sentences, actually. Right? So that's a unified mechanism. All right, so another thing I want to say, so that's with droplet collision and all that. Then you extend your thinking a little bit. How about jets? Okay, if I have two jets hitting each other. So here's one jet, here's another jet. And then you can see with low impact inertia, I get merging, one jet. If you increase the jet inertia, you get bounce. You see that? Bounce. The interface. These are all experimental results. And then if you increase it again, it merge. Okay? Just like water. Okay? Merge, bounce, merge. And then eventually I didn't show with water, but then here will merge and then it'll shatter, basically. So there's total analogy with droplet and jet. As physically you would expect that. All right? So it's nice to show this. What's interesting here is, again, you can see that this is very low inertia merging. And you can see that the characteristics is quite different. Right? They basically, the inertia, the direction of the injection angle becomes irrelevant, and they just attract each other horizontally. Okay, so the internal remarks. So droplet collision is a multi-scale, multi-physics problem. The functional theory is in place, all right? The controlling physical process, you have to remember you have to large droplet deformation in elastic collision, okay? So the viscous loss through internal motion. You have, remember, it's rarefied flow in the gap, and surface van der Waals force, it's essential for complete description, right? So the theoretical result basically agree well with experimental observations. So that's rather nice. Right? But that's one thing, you know, that one thing I want to also emphasize, I think the student too, that that's a fun part in doing research. Right now, research, you know, used to be research this experiment as theory, not as experiment theory and computation. Right? But then, so experiment is always important, right, to support the calculations. Okay, so let me give you some transdisciplinary example. Okay, I talk about this. One is the liquid phase mixing in geode hypergolic propellants. So what is this? It's a green propellant. Green propellant is gelling liquid propellant, reduces vapor pressure. So what is this in rockets and all this? You have fuel and oxidizer. Okay, they come in. Normally they'll vaporize. They'll mix, then they'll burn. Right? Now, a lot of those propellants, they're toxic. Right? They're toxic. It's no good for the people handling it. So they want to, basically, it's what's called grain propellant, they want to reduce the vapor pressure. So they reduce the vapor by putting in some gelling agents, make it more viscous. Now, the problem with the gelling agent is that then the vapor pressure decreases. So they come in here, they don't vaporize too much. So they can mix. They can mix, they cannot ignite for those propellants. So then the idea is that you want to get the two jets or droplets come and they collide and merge. So the reaction occurs in the liquid phase rather than the vaporize occur in the gas phase. Okay? So that's what, you want them to merge. So, but then the main thing is they have to mix rapidly upon merging. All right? Now, but then, of course, we just demonstrated to you. The droplet merging versus bounce is not monotonic. So if you put them in that, if they bounce away, then they won't mix. Your rocket won't work, right? Especially under high pressure, it bounce. So how to do it? So then you need to identify regions of optimum collision. So let me show you this. So what we have found, this is beautiful, beautiful experiments. It's fun doing experiments. It's fun with combustion, okay? For combustion, you can see what's happening. You can see flames. You can see things like that. So I have a large droplet and small droplet, right? So I use one to hit the other. So look at that, okay? So look at this. Then they merge, and merge, and merge, okay? The small droplet and merge with this one. Okay, it forms a cap. It's okay. But after a while, it gets discontented. Oops, it forms a jet coming out. Okay, so the surface tension force is converted into inertia of the jet, goes in. And then the jet, here you're talking jet mixing. With this one. Now, if you increase the inertia, you come here, no jet. Okay, then you get dissipated. The reason here is just there's too much deformation here that takes away the energy. However, if you increase it further, look at this guy. Increase the inertia further, hitting harder, oops, you form a jet again. And it's a different kind of jet. I mean, if you look carefully. Right? This is sort of what we call one-leg jack. This is two legs jack. So there's something here. So it's really fascinating to do this. And so that's one thing we learned, interesting. Another thing we learned is kind of really obvious, but it's this thing can happen only if there's a small droplet, big droplet. Normally, when people do research, you like symmetry. Right? When we do research, you like symmetry. So normally you have two droplets hitting each other, same size, right? You do some. But this one, you have to have a small one, big one, because you have the same. Yeah?
Is that a Newton?
Yeah. The gel propellant Newtonian fluid. This is fine. This is Newtonian. Yeah, ours is Newtonian. Yeah, but certainly yes, I know you can do different kind of things. But the phenomena is not related to whether it's Newtonian or not Newtonian. Yeah, no, that's fine. This is just no. Actually, for this this is just water. Yeah, we can do water. Yeah, we just color it. Yeah, just color it. Yeah. It's fine. It's fun. Try to do some non-Newtonian things. Yeah, and the shear. Yeah. Exactly. Yes. But what I want to tell you is, if this phenomenon, you will not see it if you do equal-sized droplets, right? Whereas for us to research, you like symmetries. But here is that it's asymmetry. So I use this word, asymmetry triumphs. So a lot of times think of when you do research, sometimes you want to deliberately break the symmetry and then see some other thing. Okay? All right. Now, there's some other things. So this is a droplet jet impact. It's a little bit busy here, but I just briefly mentioned to you. There are a lot of problems with droplet jet impact, right? Heated or cooled surface. Droplet and spray jets used for cooling surfaces, all right? Large-scale cooling in condenser or electronic cooling. Clearly, that's something of interest, all right? Then, of course, whether the cooling occurs easily or not, it depends on whether the droplet hit here, whether they can wet the surface, or they are spread out, or they actually bounce away, and things like that. All right? And also, if the surface have high temperature, like in the internal combustion engines, your engine surface is hot, all right? Then you end up with Leidenfrost phenomenon. I don't know whether you guys realize from your heat transfer, Leidenfrost, then the droplet will bounce away. So all this, these are some experimental techniques. You can shine a light, you can look from the bottom and see what happens with phenomena. So all these are related to this. Now, also the morphology of surface. If the surface roughness, okay, you make it roughness, so that basically changes the contact angles, and texture surface will affect merging and bouncing, all right? And it's clearly the surface morphology and affect the cooling efficiency. And another thing of interest that the Army is very interested in it, design of non-wetting clothing. Right? They want to have clothing which have different texture, so that when the rain drops, go away, and wet. Right? So there is practical implications. And then this inkjet printing thing, we actually got a small funding from Xerox Corporation in studying this kind of problems. One thing, say, for example, binary systems, okay? In material synthesis, you can merge and mix two liquid bodies and then forming new materials. Inkjet printing, okay? You can have different A and B, different colors. One go into here and then form one, and the next one comes here and somehow mix them. Okay? Things like that. So that's and also medical applications. So laser in the ultra-fast jet for drug injection. So what you have is rather simple. You can have one jet coming in which pierces through your skin. Okay, it sounds awful, but that here doesn't hurt. Very tiny drop. It pierces your skin, and then you have another jet coming right away, and then deposit your medication at the controlled depth of this. All right, and then this one that's so precise. You can control the penetration depth, and then also there's no back splashing, so no cross contamination. All right, so those are the possibilities people are interested in. Okay, all right. So that's one topic. Let me go to the next topic. Watch the time. Stability and morphology of expanding spherical flame. So wipe the droplet out of your mind now. I'm talking about flames, okay? So what I'm showing here is you have a combustible mixture. You spark ignite it, right? And then you have a flame propagating, right? Spherical. Right? The flame propagates very fast, so buoyancy has no effect, really fast. So that's what you see here. Certain times, you can see, you use Schrodinger's picture, you see the density gradients different. Very nice here. But certain times, you see the flame, it develops wrinkles. Okay? Rather than very nice smooth surface, it develops wrinkles right here. So, something. And then, so you have smooth flame, you have cellular flame. And then if certain time, if you look at it close enough, really high-speed movies, all right? Look at this. Isn't it beautiful? There are spirals develop over the surface. Okay? All right? Over the cells. Spirals and target pattern. Target pattern is when the cells, they are not spirals. They are closed circles. All right? So that's the kind of interest we have. So here, let me just very briefly present to you sort of the mechanism in how the flame front can become unstable. There are basically three modes of instability. Okay? One is the obvious one, the Rayleigh-Taylor instability. Rayleigh-Taylor instability is that you have a flame here with heavy gas, light gas. Okay? For example, the flame is propagated this way, so up is heavy. This is the burn gas, it's light. Gravity this level. And then Rayleigh-Taylor instability, obviously, it'll make it unstable. Okay? You guys know that. Heavy density and the light density. So that obviously occurs. Now, another mode is called the hydrodynamic instability. don't worry about buoyancy now. Any kind of flame, if you wrinkle it, a flame surface, if you wrinkle this, then you can see that it increases the string tube area here. If the flame is sitting here, flow coming here. So you increase the same. So the flow velocity here is less because the increase in surface area, increase the whole surface area. And the velocity, flame velocity, if you assume it's the same, then this will be bigger than that. So if you wrinkle it this way, it'll always propagate forward. If you wrinkle this way, it'll always propagate this way. Okay? So based on this consideration, that's what Landau did in the late 1940s, 1930s. Then all flames are inherently unstable. Okay, that's called Landau instability. All flames are inherently unstable. That's what he said. So that's one thing. Now, there's another mode, is diffusional thermal instability. So for here, you look into the flame structure, actually. And then you look into the relative rates of heat and mass diffusion, right? What's called the Lewis number. And the Lewis number actually is not 1, right? It's close to 1, not 1. So if you wrinkle this way, if your thermal diffusivity, say, is less than mass diffusivity, right? Then your thermal diffuse, if you wrinkle this way, then one will go this way, the other go this way. When it's this way, then it'll become unstable. Otherwise, it will go stable. Okay, Lewis number less than 1 is unstable. Lewis number bigger than 1 is stable. And also, you can do some kind of arguments in terms of pulsating. In terms of instability, there are 2 modes: cellular, that's spatial; pulsating, that's temporal. So it depends on the diffusivities. So without considering this gravity, you have 2 modes of instability, basically, the hydrodynamics and diffusion. Right? That's what we're talking about. So let me show you what. So let me explain a little bit to you what's happening, and that's real. Okay, those are real phenomena. This is experimentally. So again, let's look at this. I have the hydrogen case, 5 atmosphere, and the Lewis number is less than 1. So I just told you it's unstable, Lewis number. So you can see that it develops these wrinkles. All right. That's for the Link case. When it's for the rich case, the Lewis number bigger than 1 because the controlling species changes from hydrogen to oxygen. Right? It's rich case, and it's stable. Right? Unstable, stable, and unstable depend on different Lewis number. Right? So a flip side of this is instead of doing the hydrogen, I do propane. All right. If I do propane, here the hydrogen is more volatile than oxygen. Here is propane is less volatile than oxygen. So the Lewis number flips. So if I do the flipping, then for the Link case, it's stable. Whereas for the hydrogen, the rich case is stable. And for propane, the rich case, it gets unstable. Okay, so this basically demonstrates what I said about thermodiffusive instabilities. So they flips, but it's describable by the Lewis number effect. What is particularly impressive, though, is for this case at 5 atmosphere, okay, for rich case, it is stable, right? Smooth. However, if I increase the pressure to 20 atmosphere, then it becomes unstable. The Lewis number is all bigger than 1. Okay? From the hydrodynamic point, from the thermodiffusive point of view, they are the same. But when I increase the pressure, it gets unstable. So what is happening here is that I'm switching. This guy comes into question. When I increase the pressure, the flame gets very thin. The flame gets very thin, this hydrodynamic instability kicks in. All right, so you have 2 modes. And I know it's a little bit confusing. I'm flipping several things. But this is important observation. So you get this. Okay, even Lewis number bigger than 1, it's unstable. But this is due to hydrodynamic instability. This is due to diffusional thermal instability. There are 2 modes of instability. So similarly, for the propane case, link case is stable. Also link case, but when you go to high pressure, it's unstable. Okay? All right? So all this. Now, here, let me just say one thing. Maybe I'll say it again. This has significant implications. What this means, that's my conjecture. I've been, it needs to be proven more. All flames in internal combustion engines are unstable. Okay? That's a big statement. All right? Because people always say that in internal combustion engine, you get turbulence, which you wrinkle, my friend, which changes the surface area. I say in addition to turbulence, the flame front instability is inherently unstable also. You need to watch out about these wrinklings. Because the internal combustion engine, the pressure is high. You go to diesel engine, 50 atmosphere. Right? Here I only have 20. Right? So they are all unstable. So if you do CFD simulation, all right, Professor Weishi is the expert in this, you have to allow for this kind of instabilities to properly describe the frame front propagation. So that's something. Okay, so I want to show you some other things. It's really beautiful. You look at this. This is, I want to show those spirals and pulsating instability. Look at this. This is what people call targets. It's a closed circle, like a target, right? You can see that. You're taking at 15,000 frames per second. Within consecutive frame, it comes here. Those targets, come out. Okay? Beautiful. Huh? Beautiful targets. And also, then you get spirals, which I showed you before. Okay? Spirals is a form of targets. Spirals are this sort of imperfect targets. Targets, they will close. Spirals, they don't close. Okay? So you get targets. And also you get disordered spirals. Huh? That's really rather, again, as I said, rather interesting things. And, I really don't, so this I'm just showing pretty pictures. The practical application, I have to, have to think of some more. I think it's practical application. One thing is it's usually those kind of system pattern occur when the flame is about to extinguish, when they're burning very weak. I think those are if you can diagnose, you can monitor the flame propagation. If you see those kind of happening, you see the flame is dying. Okay, let me quickly do something. Okay? Quickly do something to stop it from dying. So those are the things I can think of. Now, another thing, as I said, expanding flame would eventually trigger this hydrodynamics. It's called also the real slender instability. Okay? What's the significance of this? I go back to this cellular flames. What's the significance? Continuous evolvement of cells will increase the surface area. Okay? Right? So when they increase the surface area, they will increase the propagation speed. So therefore, if I characterize the radius of flame as t to the alpha, then the flame speed will go t to the alpha minus 1, right? So if alpha is bigger than 1, the flame will accelerate. So self-acceleration. It'll keep on going faster and faster, okay? Now, if alpha is in addition to constant, then the propagation is self-similar, have a fractal character. Okay? Fractal. So then again, even this instability says it's promoted with the increasing pressure. Pressure is a big factor here because of reduced flame thickness. So this fractal character, so we've been chasing it. And this, of course, the big, deep meaning, what do we mean by fractal and all this, okay? But straight from definition, that's what this is. So, and other people have been doing too. So self-acceleration could lead to what's called self-turbulization. If your alpha goes to 3/2, this is the fractal dimension of Kolmogorov turbulence. Okay? So that's one point. So as a flame goes, remember, it's a laminar flame. It's a quiescent atmosphere. It's laminar. Even it's wrinkled, it's laminar. Okay? But then it can go to maybe conjecture, it can go to become turbulent. Okay? So you have a laminar transferring into turbulent behavior, which is kind of interesting, right? From ordered system into chaotic system. Okay? So, and then, again, conjecture. If it keeps on increasing, eventually, maybe it'll self-detonate. Okay? Then you go from subsonic burning to supersonic burn. So it'll go on, it'll explode. Right? In unconfined space, not a confined space. If it's confined space, it will, because the overall pressure increases. Unconfined space, can it go? It's $1 million question. All right? I'm still chasing it. I can't find it. I just don't have, I need a bigger environment to make sure it's sort of free. So previous results there, I don't want to say the previous results are not correct. So we have done some experiments. Don't worry about this. So I try to increase the pressure, try to increase the burning rate, try to tease out the behavior. And one thing I've definitely demonstrated is the velocity of the flame as a function, okay, of the radius. As it goes out, average radius, this definitely is increasing, okay? This self-acceleration, that definitely we've demonstrated, self-acceleration. And also seem to be locally similar because it's a sort of straight line, right? So alpha is constant. So this is something we have done. But we have not done, I cannot demonstrate self-turbulized. I have not gotten into this particular value. I have not demonstrated. Don't worry about this. So I have not demonstrated it could self-turbularize and self-detonate. Those are the things we haven't done. We're chasing. But I've recently built a much bigger bomb at Tsinghua University. They have more resources than we have in America now. So I'm trying to see that. Okay, so these are the internal remarks. Are all flames inherently hydrodynamic and stable at elevated pressures? Okay? I believe so. I believe so. If so, it serves as an additional mechanism in flame wrinkling when modeling turbulent flames. All right? Is flame acceleration self-similar? Is self-acceleration a mechanism for self-turbulization and DDT? DDT is deflagration to detonation transition. Okay? Elaine Oren is very interested in this problem. I know she visits here sometime. That's a problem she should be chasing too. DDT. Free space. It has to be free space. So what are the practical implications of pulsating instability, such as spirals and targets? Don't know. But they're nice. So now some transdisciplinary examples. Let me do that. Okay, about instabilities. How am I doing in time? 4 o'clock. I'm okay, timing-wise? 15 more minutes? Okay, let me, 15 minutes. So, one is material synthesis, okay? Material synthesis, for example, one thing I want to impress upon you, combustion people, hydrocarbon burning, you're only dealing with 3 elements, carbon, hydrogen, oxygen. You look at the table of elements, you got 92 for the stable things. If you just think of, you can combine one on the left-hand side, one on the right-hand side, you can make all sorts of materials. Isn't it fun? All right? So there's a lot of potential into material synthesis with combustion. We haven't done too much. Now, one thing is, for example, you can do solid flames. Solid flames, you have 2 sort of solids, pack them together and get them to propagate down. Right? One thing of interest is that these are large Lewis number flames. So actually, when they propagate, they pulsate in the solid phase. Go this way. So you get laminated structure. Okay? So it's not very good. So that's one thing. Okay. Inertial confinement fusion. It's a big problem in inertial confinement fusion. You can argue, you can see that you have a pellet here, you have a laser coming here, you get the plasma, you try to compress the target to cause a nuclear nuclear reaction, all right? But the whole problem here is hydrodynamic, Rayleigh-Taylor unstable, all right? And that is the problem in inertial confinement fusion. You cannot focus it to get it done. Pattern formation in biological systems, all the spirals, it's been observed in many things. In slime modes, in slimes, you get this, developing OSS, that's in ladies, the ovals, they get this surface. Cardiac muscles can develop these spirals. Chicken retina suddenly go this kind of things, like spirals, all right? And similar to what we have observed in the surface. All right? Nice. And also fronts, natural societal fronts. Forest fires, they're front propagation. Leaching spreading on the rocks, again, spreading. And the spreading of bubonic flags. They're all fronts spreading out. You have this kind of disease, okay? And the population spreading. They're all fronts, just fronts, okay? Okay, all right, I have 10 minutes now, right? 5 minutes?
15
still 15? Okay, good, just give me more time. Okay, so development reduce all the reaction for large-scale computation. Okay, so I'm to the topic. So hydrocarbon oxidation, it's very complex. It's large size, stiffness, and non-monotonicity. So if you think of hydrogen oxidation, right? Your high school chemistry, 2H2 plus O2 go to 2H2O. Never happen, believe me. You don't have two hydrogen molecule and one oxygen molecule. They agree with each other. They meet at the same point, they react, and no way, okay? So what's happening is they go through a pretty complicated reaction. There's 19 intermediate reactions. A lot of intermediate species. There are 8 intermediate species occurring, okay, here, and then they react. And then the response, if you look at the temperature and pressure region, for given temperature, if a low pressure, it'll explode, no explosion. Then it'll react, explosion. You increase pressure further, no explosion, then explosion. Okay? So that's the chemistry for you. All right? And we can explain everything here, no problem. Now, the problem, of course, is the size and complexity. The size, this is the growth of hydrocarbon oxygen mechanism size. Number of species and number of reactions. Here is for the methane. Look at this. Huh? This is slightly less than 100. Huh? Here is more than. This is one order higher number of reactions. And then you keep on going. These are the biofuels. You go into almost 10 to the 4th. And this one go to 10 to the 5th even. Okay? Huge number. No way you can do CFD with this. No way. Okay? No way. Too big. This. So not only size, but they are also stiff, extremely stiff. The orders can go 10 orders, chemical reaction, 10 orders. There's no way you can trace. And also you have to do the turbulence. You have to handle the turbulence. They are also stiff, okay? Also large scales, no way. So they are, of course, if you look at it, they are just reaction networks. This hydrogen-oxygen system, you have all the species. Look at this, H2O, 2H2O. Now, I just want to show you, if you don't know chemistry well or not familiar with, you have HO2, okay? Those kind of funny molecules. It's not H2O. It's not a typo. It's HO2, okay? They are very important. And then you see how they react. And this is just hydrogen oxygen. Look at methane oxygen, okay? So people have been doing this and look at this through a reaction network analysis, and then try to look at what are the dominant pathways. So through that, they can simplify the problem to a certain extent. Right? So I'm not going to go into this. They can do that. But still, there's a lot to do. Right? Let me see. So the computation is essential for complex, multi-scale, highly coupled nonlinear problems, okay? So the breakthroughs, they are facilitated with a broad knowledge in mathematics and computation science. So one big advance in the last few years is use of the graph theory in mechanism. Right? Basically things like that. You analyze through as a graph theories, okay? Through the graph theory to do that. So you need to know the mathematics. And that's a message I want to give to the students here. You need to know the mathematics, okay? Don't skip the math course, all right? Okay? Take your math course seriously. That's how we did that graph theory. The student got interested, he said the math got something. I said, okay, go ahead and look into it. And that turns out to be I think probably the best method so far. So, yeah, okay, never mind with this. Transdisciplinary or network analysis. Oops, what did I do? Okay, network analysis, you can apply to biological systems, system biology of human aging. Okay, look at this. This is really complicated. Large numbers of objects, organs, tissues, cells, molecules. It's different biological systems. You try to analyze that. Okay, network. Social networks, your Facebook. Okay, traffic network. All right. So, all right, it's you know the thing, and then you can apply it. All right. So let me go to the last topic. I'm making good time. Making some moderate time. Dynamics of detonation. What do I have here? A terrestrial example. Recently, past few years, there's a big, interest in internal combustion engines. Because of they want to develop engines which, through the burning process, that, in engine combustion, there's knock in engine combustion. If the fuel isn't good, your engine isn't good, when you press on the gas pedal, you hear this ringing voice. That's detonation. That's knock, okay? So knock is no good. The detonation engine, they damage your engine, okay? So the regular detonation, the conventional knock, they sort of melts your piston head. So you got pits, okay? So your engine is not too good. After a while, you take apart the engine, that's what you get. But recently, there's even more serious. With the new fuels and new development engines, you got what's called super knock. It just happened, bam, just one knock. Your whole engine's broken. The whole engine is broken, okay? That's what happens. And then what people have observed is there's really very strong detonation occurring inside the engine, all right? So there's some very strong pre-ignition and all that. It's a very active area of research, all right? So this is sort of what detonation do to you. So that's one thing. Now, so as terrestrial example, let me give you about detonation. Right? Let me give you extraterrestrial example. Okay? Chinese here. I have to put in some Chinese here. So detonation of Crab Nebula shock front. Crab Nebula was first observed by the Chinese astronomers in 1054. That's our contribution, the Chinese contribution to the world of astronomy. Right? So people in the modern observation data, they've observed it. They do some extrapolations. They say, look, it seems it's much later, 1130. Okay? But when you look at that, you say, okay, here's the really historical indications of this Crab Nebula. So, but they're assuming constant expansion velocity. So what we have thought is, look, I mean, it's not constant because this detonation wave, it could accelerate. So you do the shock wave formulation, but it's a detonation. They assume it's a shock wave, but we say it's really a detonation. Okay, there's a difference. That shock wave is just non-reactive. Detonation is reactive. You put in the detonation, and then you do the analysis, it seems it explains rather well, how, with the time. Right? So that is just a sort of small contribution to this. We are chasing very much on the supernova. Really try to explain the supernova. There's no way. So many brilliant astrophysicists are working on this problem, supernova. You can explain that, one Nobel Prize, definitely. I can guarantee you, okay? I mean, the physics guys will guarantee. So anyway, I just want to show you it's really, really rather, this sort of self-turbulization, self-detonation, how it goes. Because this supernova is that they can sit here for millions of years. This star, millions of years, nothing happens. And suddenly, pah, a few seconds, it explodes. Okay, that's violent. After it explodes, the remnants will stay there for a few years, very bright. Okay, what they say, if any one of you is a Christian, in the Bible, when Jesus was born, there's a bright star, supernova. They have chased through around that time. It's a supernova, bright star. So summarizing, so I'm coming to that. So summarizing, so the core combustion phenomena which I discussed is droplet collision, surface morphology of propagating flames, dimensional reduction and reaction mechanisms, the dynamics of detonation, all right? And the transdisciplinary combustion topics which I mentioned, inkjet printing, medical injection, surface wetting, cooling, material synthesis. I covered it real fast, I'm sorry. Inertia, confinement, fusion, front dynamics, network analysis, supernova. Isn't it fun? Huh? And what I want to emphasize is that to get to the understanding, you have to involve theory, computation, and experimentation. All right? I've always encouraged my students, we do all three. You have 3 tools in your pocket, more powerful. At least you should know 2. Either computation, experiment, computation theory, or something like that. It's 2. If you can do 3, it's even better. Okay? Tools. And then I emphasize that math is essential. You have to do that. So combustion is rich in physical phenomena, from fundamental to practical, from terrestrial to extraterrestrial. Isn't it fun? So expand the mind, be curious, be bold, and have fun. Okay? That's the most important. Be happy. Thank you very much.
Yeah, for your drop collision case between water and hydrocarbon.
Oh,
go back to the basic.
The drop, it's just water, same thing.
Yeah, so what are the additional defining parameters you use?
Okay, you need to know the inertia, right? Inertia, and then inertia. That means the droplet velocity and the size, right? The properties of the thing are the surface tension, viscosity coefficient. That's important.
So if you have a Weber number, you have capillary number.
I have Weber number, capillary number. I can describe somewhat, but I cannot go to the final result for them to merge. For them to merge,
something else is missing.
I can describe bouncing. For them to merge, I need the van der Waals force, so that the molecular attraction. I don't have it. Right? Now, if you really want to be accurate, then you have to describe the dynamics of that. That goes to your what's that number? The rarefied flow. Yeah, that's it. Rarefied flow. So you need to do that. But just the bouncing is actually easier. Bouncing is easier. But then how can you say it's bouncing? You have to say it's bouncing so that it's not merging. Then you can do something.
So because if you use the rarefied gas effect, then there are some others parameters that need to be introduced.
Sure.
So people use usually Weber number and the collision number, right? Then you have it's not enough.
Not enough. Absolutely not enough. Yeah. Absolutely. So what people have done, we have published our experimental result, people have simulated, is that they have to put in given input the instant of merger. Then the bypass the unknown. Then the simulation all agree very well. Okay? You let it collide, and you say, okay, at that point, I break the surface. And it's okay. But that's a little bit cheating. Right? I shouldn't use the word cheating. But there's no way. It's hard to do.
That's where your continuum model does not work anymore.
It doesn't work anymore. And it's important because we have done some calculations. You have to treat it as rarefied. If you treat it continuing, it doesn't agree. Because, because there's a lot of deformation around there. There's a lot of viscous loss. You are losing your total energy conservation.
The other thing about your flame stability.
Which one? Flame stability.
Yeah, the turbulization.
Yeah.
Has there been any measurement in terms of the spectrum? Because
not yet. We are trying to do that.
That is the key to tell whether you
exactly
right?
Exactly. Yeah, exactly. What I said is really very, very gross. You say, okay, there's this parameter and things like that, but eventually you have to. We are developing that. Yeah, it's a self-turbulization. I don't know. I hope self-turbulization.
Sir, in droplet collision case, I think instead of using, multiple stages like Navier-Stokes and in computation, if there is a rarefied regime, instead of all these, we can use one Lattice-Boltzmann equation which can explain both transport and collision.
Yeah, you can try Lattice-Boltzmann. People
because the merging can be
totally. Yeah.
Merging can be explained by collision and sorry, merging can be, yeah.
He's the expert, Lattice-Boltzmann. I don't think it's...
Okay.
It all depends on what model you put in, right? Because if you use PGT model, then you already truncated, so you have limited applicability.
Yeah.
How do you balance your interest, your own interest and the industrial application?
Industrial application?
Yeah. So for example, you have done lots of theoretical research, but how do you apply fundamental things? How do you apply those?
Look, my droplet, what is it? My ink droplet thing is interested by Xerox. That's practical, right? They're very practical people. They give me some money.
The answer to that is use
Right.
industrial money
Okay,
to
so
do
for research,
fundamental-
So there's no. Let me put it this way. Do not apologize to do fundamental research, you guys. Okay? You hold firm in the usefulness of fundamental research because that is one that drives the discovery of new phenomena, new applications, and all that. Okay? Don't apologize when you go to say. You say that this is important. You have to have a strong conviction to that, and which is not you just try to sell it, but you truly believe it. You look at there's a lot of smart people, of course. They, from the practical point of view, they do things, but eventually a lot of this, especially nowadays, to really make frontline discoveries, a lot of it is still you come from the basics. You come from the basics. Okay? But that's it. That's all. I mean, so I give you all those examples. I give you all those examples. You just have to be very, very. I shouldn't use the curious. Just to be very open. Very open, right? And then read the science magazines, right? Just be more exposed to what's happening, right? Journals and then talk to your other friends working in other problems. And then suddenly you make some connections. Right? But you have to be disciplined. You cannot be too wild. Things have to be based a little bit on the principles. Right? Yes.
So why these population growth patterns look very similar to the combustion pattern?
No, what I'm saying is just this front, right? There's the front, and then you have to look into the driving force in whether the propagation is stable or is non-stable and things like that. So there's different mechanisms, different mechanisms. I'm not saying it is similar to.
Because they seem to be looking at very different scales.
Yeah. So again, all I'm saying is just the front.
If you write down the governing equation for the front dynamics,
Yeah.
in fact, they're quite similar.
Yeah.
Between phase change
Yeah.
and the flame front.
And the
Gross
stability.
media flow. In
Yeah.
fact, they're all governed by the same equation.
recently, like this kind of complex systems approach is emerging. They bridge all different systems like biological system, chemical systems, all behave in a similar way. That is what they are bringing, like a universality, like despite the difference, physical difference in details of all the systems, most of our biological and engineering, all the natural systems, like striking resemblance are there in their response. That's what they are trying to bridge in this complex network analysis and complex systems analysis. This is happening only in last 10 years, since 2000.
Yes. Yeah, thank you very much for your talk. I have a question about the study of droplet impact of the thing. So you think the pressure is very important, right, to differentiate this kind of water and also hydrocarbon? Yeah. But my question is any way we can normalize this key parameter of pressure so that you can collect all the data?
Yeah. That's what Professor Wei Xu was asking. Eventually, you have several parameters. You will have several parameters, clearly. It has, what should I say?
It's not only the droplet, but also the flame.
Yeah.
The flame has a
flame.
The pressure is really. Huh?
No. I don't know. Flames, that's a little bit too ambitious with flames. with droplets, eventually there will be some. It hasn't, you can just write down, right? So many parameters just form so many non-dimensional numbers, right? The Weber number and several other numbers, and they will be properly represented. But this is quite a few numbers.
Also one more question about the droplets. So some are bouncing off from each other, some are merging into each other. So is the polarity of the
Polarity, of course. Polarity, of course. If you have water droplet and hydrocarbon droplet, water droplet is polar, hydrocarbon droplet is non-polar, and it's very funny, they don't mix, right? Yeah, so that's a different issue now. Then you try to, your interface relations. You try to, now this is something which isn't really totally understood. People have done that. Very interesting. Water droplet, hydrocarbon, when they do this, they don't mix, they don't bounce, they just sort of stay with each other this way.
But my intuition is on the contrary, so the other way around. So it's like when they are polar, then they
two polars.
Two polars can merge into each other.
So there will be additional force. I think this is just a different force, different surface, different molecular force. That I think it can be. Water and water, right? That's polar and polar. So that's yeah. Water and water is polar. I was thinking it's polar and non-polar. Polar and non-polar, do they merge? They merge, right? Or because they normally won't merge, right? But experimentally, we found that they can't explain yet. They just come here, they don't bounce, they don't merge, they just stay there. Something you can check. Yeah, it's kind of, yeah.
So, one more question is, I don't know if possible if we use those the theory of nonlinear dynamics of calculus to study this kind of very complicated nonlinear, like a chemical reaction flow. In nonlinear dynamic system, we have some theory. For example, we started the improved exponent analysis and characteristic section analysis to dimensional reduction. So I don't know if you or anyone tried to do this kind of analysis about your...
For the nonlinear system?
Yeah, right? Nonlinear dynamic system.
Then what?
We can study the...
Dimensional reduction.
Yes,
right?
yes. There's a family of theory. Actually, like 20 years ago, I used this one to study the chaotic mixing.
Chaotic mixing?
Yeah, actually it turns out it's useful. We can start the mixing.
I cannot answer that question, but certainly it's interesting. It's chaotic.
Yeah.
In thermal acoustics.
Yeah, I should.
You can do this. Yeah.
So basically,
we need all the help.
Because the linear dynamics theory actually explain about the chaos, right? And it turns out the improved exponent actually is related to this kind of mixing in terms of fundamental theory. Yeah, I done this. It's very interesting. We can really compare theoretical work with experimental data in our microfluidic device. Yeah. I can give you my paper.
You can have to hide it, otherwise.
Yes.
You have to combine that.
Yeah.
Yeah. Take a look.
Okay.
Yeah. Maybe you will send me your paper. I would like to take a look. Yes. Yeah. That's why I emphasize transdisciplinary. You know, it's very once you started going here, going there, you suddenly pick out the spring and then.
In general, for flow mechanics or thermal fluid, they don't study this kind of nonlinear dynamic system.
Mm-hmm.
So but okay, I can give you my paper.
Yes. Yeah. I mean, for the students, that's the fun of doing research and the fun of just thinking out of the box and to learn from others, right? And then there are just so many new ideas once you go away and then.
Dear Professor Law, thank you so much for impressive lecture. We three guys from the Chinese University of Hong Kong, and I have one question. I just didn't see the relationship between the combustion and the social network. Can you please just elaborate a little bit?
No, I'm just saying this are all networks. Yeah, they're just networks, and then you just like you do your network analysis. Right? There's a lot of analysis. Traffic networks, where your bus goes from here to there, or the air, the airlines.
That's analogy, right?
Yeah.
Perhaps Nina, would you like to?
It's actually like in social network, if two people are connected, they are like linked in the social network. In combustion, he had shown a lot of species, right? Yeah. If they are reacting, it is forming links. So you can bridge two different things in a common platform.
How would you comment on critical Lewis number?
Critical
Lewis number.
Oh, critical Lewis number is Lewis number is basically whatever you define it, thermal to mass. The flame behavior actually flips when this is thermal is bigger than the mass or mass is bigger than thermal. It's very easy to think of why, because if you look at the flame, the thermal is away from the flame. It heats up the gas mixture. Mass is towards the flame. Okay, so if they are of the same rate, then everything is conserved. Okay, because your total energy is the thermal energy plus the mass. Mass is the chemical energy, and it's conserved. If they are off balance, then it's not conserved. Not conserved locally. So the burning intensity would suddenly weaken or more intense. It's 1. Oh, close to 1. No, I'm not saying 0.92. Why do you say 0.92? No. It's not 0.92. You're probably thinking of stoichiometric or something. When it goes off stoichiometric, when it goes to lean, the controlling mass is the fuel. When it goes to rich, the controlling mass is the oxidizer. Okay? So you can flip between less than 1, bigger than 1. Less than 1, bigger than 1. You don't have to flip too much. If you go with, because your flame temperature is directly proportional to the deviation from 1. Okay? If it's exactly 1, you have the adiabatic flame temperature. If you are off by 0.01, 1%, your flame temperature is off by 1%. When your flame temperature is off by 1%, your Arrhenius factor, the exponential factor, is off by maybe order 1. So all you need to do is just change a little bit. That changes your flame temperature, and then it causes the whole flame to go unstable. Yeah, so that's why the flame temperature is so important. Right? That's fundamentally is the conservation of total energy. Right? And then through the kinetics, it makes the flame go. So that's for the diffusion of thermal instability. Hydrodynamics is a different one. Right?
Okay. So if we don't have any further questions, let's thank our speaker one more time.
My pleasure. Thanks.